Sulfuric acid, what's the formula for sulfuric acid? H2SO4, good. And ammonium acetate? There are two ways of handling this. One is, this looks like what kind of reaction? Double replacement. If it's double replacement, we take it all the way. So this one will do metathesis, double replacement. And so what's going to form? It's going to be ammonium sulfate. Ammonium sulfate, ammonium's a +1, so we'll need two of these to balance out the -2 of sulfate. And hydrogen acetate. Hydrogen acetate is also called acetic acid. We have a driving force here. What would the driving force for this reaction be? Yeah, stronger acid to weaker acid. What's the weaker acid in this case? Is the weaker acid ammonium? You know, ammonium's a weak acid. Would the weaker acid be ammonium or acetic acid, or both? Sometimes the weaker acid is ammonium, but in this case it isn't. Because if you look at ammonium, nothing happened to ammonium. So we had ammonium on the left, ammonium on the right. And so the only change here is going from the stronger acid, sulfuric, to the weaker acid, acetic here. And so since there's a driving force, we'll go ahead and balance it. We'll need 2 ammonium acetates and 2 acetic acids. And then it's balanced. So the forward direction is the direction preferred. Reaction. The other way of dealing with this is via the chart method, the Bronsted acid-base method. If we do it the Bronsted method, then it's done a little bit differently. When we use the chart method, first we inventory. And so when we inventory it, H2SO4 is going to give us what in water? Yeah, we're going to have H plus and HSO4 minus. And then ammonium. And then acetate. And then water. H plus is acid. HSO4 minus is acid and a base, but the base is so weak that it's negligible. It's like chloride. Chloride is not much of a base. And so this is much better acid than a base. But since it could go both ways, we'll just call it base. Ammonium is an acid. Acetate is a base. Water is both an acid and a base. Water is pretty much equal in terms of strength as an acid and a base. These ones that are so weak, most people ignore the base properties of it. So which one's the strongest acid? Do you need the chart for this? No, we don't. H plus is going to be the strongest acid. H plus or hydronium. Which one do you think is the strongest base? Acetate. So the reaction will be between H plus and acetate. This is going to form acetic acid. And we see that H plus is a stronger acid, H plus or hydronium, and acetic acid is weaker acid. So this is the same driving force. In Chem 1A, we only do one step. In Chem 1B, we might do a second step. Because after we consume the H plus, then what's the next strongest acid? So once the H plus has been eliminated, then the strongest acid would be between HSO4 minus and H4 plus. It turns out HSO4 minus is a pretty good acid. And so this is step 1. Step 2 would be what's left over. What's left over is HSO4 minus. That was the second strongest acid present, but now it is the strongest acid present once H plus has been eliminated. And it's strong enough to react with acetate as long as there's enough acetate around. And so if we have enough C2H3O2 minus, then what will form is acetic acid and sulfate. This would be step 2. And so HSO4 minus turns out to be a stronger acid than even acetic acid, so there's a driving force for this. And so we handle it a little bit differently, metathesis versus Bronsted. In Bronsted, we just do one step, or one step at a time. Yeah. Now, if we have metathesis, this is the CE, and then we have to do the IE and the NIE. So the situation is whenever we use the chart method, we end up with the NIE. This is the NIE. So if we want the CE, we have to work backwards from the NIE back to the CE. Over here, we'll just work forward. If we do double replacement, we should do the IE and the NIE. So H2SO4 is a strong acid. Acids are strong electrolytes. So what do I break it up into? H plus and HSO4 minus. Ammonium, we already did the inventory over there. 2 ammoniums in this case, plus 2 acetates. How about ammonium sulfate? Do I ionize that or just leave it alone? We ionize it. So this is going to ionize into 2 ammoniums and 1 sulfate. So 2 ammoniums and 1 sulfate. Acetic acid, do I ionize that or just leave it alone? We leave it alone. It's a weak acid. Weak acids don't ionize. And so what's the spectator? It looks like the only spectator here is ammonium. Everything else appears to react. So it's going to be H plus HSO4 minus plus 2 acetates yields 2 ammoniums plus sulfate. Oh no, what am I doing? No ammonium. Ammonium spectator yields sulfate plus 2 acetic acids. So there's no precipitate, there's no gas formation. Sulfuric acid is a CCS, ammonium acetate's a CCS, ammonium sulfate's a CCS, and acetic acid, sulfuric acid and acetic acid are both CCSs. So I'm not going to see any gas formation, and I'm not going to see any precipitate. And so how can I tell if a reaction occurred? So here's my ammonium acetate. This is CCS. Let's pour a little bit in here. And then here's my sulfuric acid. It's also CCS. And then I add the acid. I add the acid slowly, in case what's generated. Whenever you add acid to water, some heat's generated. And so in this case, I'm going to add it to my ammonium acetate. And I expect this metathesis or acid-base reaction to occur. And then the test tube is a little bit warm, not that warm. It's just a little bit warm. But I have a CCS here. One thing I'm going to try to do is I'm going to try to smell something. Sulfuric acid has a corrosive smell. I don't want to really smell that. But acetic acid has a vinegar smell. Ammonium acetate doesn't have any smell. So I'm going to see if I can smell acetic acid vinegar. Usually when you smell stuff, you're supposed to waft the molecules to your nose. Because if you put it right under your nose, it could overpower you. But I don't smell anything. Oh, now I do. So I couldn't smell anything when I wafted it, but when I put it right underneath my nose, I can smell a little bit of vinegar smell.
Careful.
Yeah, I should be careful. If I agitate the solution, maybe I can get more of the acetic acid to volatilize off. Okay, so there was a little bit of evidence of reaction there. This one is just ammonium sulfate and acetic acid, so I'm just going to dump it. Okay, what's next?
Well, before we were doing it where we would add like nitric acid to
The precipitate? Yeah, this one we are not doing that.
Sodium hydroxide, ammonium acetate.
Sodium hydroxide and ammonium acetate.
Don't erase that yet. Can you do it over there? Okay. I just got to get the last part.
Okay. Let me put this up here again. Erase part of it. Someone grabbed so many black pens, but they're all dried out. Where the glue gone? Just got a new pen.
And now you can erase it.
Okay. All right, so continuing with chapter 17. We have sodium hydroxide and ammonium acetate.
Yeah.
If you can do a metathesis, then that's the way we want to do it. We just want to do a double replacement. And so, what would this form?
Ammonium hydroxide,
Ammonium hydroxide
sodium acetate.
and sodium acetate. Is that what, Rick? You should know something about ammonium hydroxide. There's something special about ammonium hydroxide. Like carbonic acid and sulfuric acid. Those three you should know. Carbonic acid, sulfuric acid, and ammonium hydroxide. What do they all share in common?
Unstable.
They're unstable. Carbonic acid decomposes into
CO2 and H2O.
CO2 and water. Ammonium hydroxide decomposes into NH3 and H2O. So we shouldn't leave this like this. We need to decompose this into NH3 plus H2O. Good. Do we have a driving force for this?
At least 3 gas.
NH3 is potentially, it's very soluble. So it's either gas or aqueous. If it's a gas, then we can say gas formation's driving force. Is there another driving force for this? Yeah, strong base to weak base, but which one would be the weak base? which one would lose the proton? So if you go forward, bases accept a proton. And if we go backwards, well, acids lose a proton, bases accept a proton. So which one's gaining a proton going backwards? Because we have a lot of bases here. Ammonia is a base, water is a base, acetate's a base. So which of those three bases reacted?
Going backwards ammonia.
Yeah. And so we could go stronger base, hydroxide, to weaker base, ammonia. And so in this case, the weaker base would be it. Or we could do the acid. What would be the stronger acid? So the stronger base was hydroxide. What would be the stronger acid? Acid's the proton donor. So who lost the hydrogen? Ammonium. So we could go stronger acid, which is going to be ammonium, to weaker acid. What's the weaker acid? Water, in this case. And so this will be our driving force. So we have driving force here. No precipitate, though. So let's go ahead and do this one. Take sodium hydroxide and ammonium acetate. And so the rule of thumb is to add the acid. And so I'm going to put the sodium hydroxide, even though that's more reactive. Just use this sodium hydroxide here. Sodium hydroxide is a CCS. And then I'm going to add ammonium acetate to this. I have over here still. Let's see what happens. All right, I don't see any bubbles of gas forming. And that's because ammonia is so soluble. You know, like dissolves like. Ammonia is very soluble in water versus CO2. CO2 is very insoluble. And that's because ammonia is very polar. CO2 is very nonpolar. Let me see if I could smell the ammonia. So I'm going to try to smell the ammonia by wafting the vapors. I don't smell any ammonia. Now I smell it. So when I held it, when I was wafting it, I couldn't smell it, but now here, it cleans your nasal passages, the ammonia. And so definitely could smell the ammonia, so some was coming off as a gas. All right, let's go ahead. I'm not going to do the Bronsted, because if we can do metathesis, let's just do metathesis and not bother with the Bronsted. Okay, let's do the ionic equation. Break it apart. Yeah, all sodium salts are soluble, so soluble salts, strong electrolytes. Ammonium salts are all soluble. Ammonia, water, sodium acetate. So spectators here, sodium ions would be spectator and acetates. I'm going to reverse this. I'll make it ammonium plus hydroxide ions yields ammonia and water. What's next? Ammonium and ammonium acetate. All right. Ammonia and ammonium acetate.
the other one? Can you erase that side, thanks.
Excuse me. Excuse me. We can treat this as metathesis whenever we have aqueous ammonia. So if we were to treat this as metathesis, we'll take ammonia and water and combine those to make a little bit of ammonium hydroxide. And that's going to react with ammonium acetate. So if I have a ammonium hydroxide plus ammonium acetate, what does it make? It would make ammonium acetate and ammonium hydroxide. Ammonium hydroxide decomposes into what? Ammonia and water. Do you see nothing happen? This is a no reaction. So, grab my test tube. I'll get some ammonium acetate and add some ammonia to that. Yes, this has a very powerful odor of ammonia. Does that mean anything happened? No.
But we could make something happen.
Could, yeah, but not with this combination.
What if we try heating it?
If we heat it, we'll just smell the ammonia more intensely. The ammonia is already there. There's ammonia there, so. Nothing happens. All right, what's the next one?
Sodium carbonate and sulfuric acid.
Sodium carbonate and sulfuric acid. So sodium carbonate is a CCS. This is my sodium carbonate. And what do you expect to happen? So, okay, let's go ahead and predict this reaction here. Sulfuric acid? All right, this is double replacement. What should form? Sodium with sulfate and carbonic acid. Carbonic acid is unstable and decomposes into CO2. CO2 is not soluble, or not very soluble, so it should bubble out or effervesce. What's the driving force? Gas formation. Anything else? Yeah. Stronger to weaker acid. So this is the stronger acid, and then CO2 is our weaker acid, or carbonic acid. maybe it makes more sense to go to carbonic acid because then you can see going backwards, carbonic acid loses the hydrogens. CO2 is a Lewis acid, so it's a bit trickier. Let's see what's happening there. All right, so let's go ahead and do the ionic equation. Sodium salts are all soluble, so we split that apart to 2 sodiums, 1 carbonate. H2SO4 is strong acid, but only 1 proton breaks off completely. The other one is kind of stuck on there until something plucks it off. Carbonate can easily pluck that off. So carbonate will take this hydrogen first, and then it'll pluck this one next. Sodium sulfate, we saw that earlier, 2 sodiums plus a sulfate plus water plus CO2 gas. Spectators? Sodium. So we have the acid, we're adding the acid, let's say, to the carbonate. And this is going to form sulfate plus H2O liquid plus CO2 gas. So I have my sodium carbonate here. I'll just add the sulfuric acid. Let's see if we can see the bubbles of gas form. Do you see it?
Yes.
Ooh, it's too much. Tried to be more dramatic there. Okay, so we have bubbles of CO2 gas and the CCS. Okay, what's next?
Sulfuric acid and
Sulfuric acid and sulfuric acid?
Sodium hydroxide and sulfuric acid.
Sodium hydroxide and sulfuric acid. Okay, let's take a look at that one next.
Let me just take a picture.
Okay. So we have some sulfuric acid and sodium hydroxide. This is double replacement. What's going to form here?
H2O.
Yeah, H2O and sodium sulfate. All right, to balance this, we'll need 2 sodium hydroxides and 2 waters. The driving force? Yeah, so sulfuric acid is a stronger acid. Which one's a weaker acid? Water. That's correct. And so we're going stronger to weaker. Okay, let's go ahead and do the ionic equation. Sulfuric acid is H plus and HSO4 minus. Sodium hydroxide is going to go to 2 sodiums and 2 hydroxide. Water doesn't dissociate. Sodium sulfate will go to 2 sodiums and a sulfate. Spectators looks like sodium, so we're going to have H plus HSO4 minus plus 2 hydroxides yields 2 waters plus the sulfate. This is metathesis. No, metathesis, you react completely. That is, both hydrogens, in water only one of the hydrogens breaks off because water is not strong enough to pluck off both hydrogens. And so in water, we'll have one H plus completely broken off, and the second one, for the most part, stays on there. But if we have hydroxide, hydroxide can easily take this one and pluck the remaining hydrogen off sulfate. So hydroxide has no problem removing that. That's for metathesis. For Bronsted, I told you, if we could do metathesis, go ahead and do metathesis. But I want to mention something about Bronsted here. This is what we call complete neutralization of the acid. We completely neutralize it with base. In this case, we remove both hydrogens. But in Bronsted, that's going to happen one at a time. So Bronsted, what are we going to have? We're going to have H plus, HSO4 minus, Na plus, OH minus, and water. There are three amphoteric species here. HSO4 minus, the base property is extremely weak, so we usually treat HSO4 minus just as acid. Hydroxide is a powerful base, but it could also be an acid to make oxide. Water can go either. And so the strongest acid is going to be H+. The strongest base is going to be hydroxide. And then we'll form water. And what we're going to be left over with is if we use the H plus in the water, we're left over with sodium bisulfate. And so this would be step one. We could stop here at step one. If we stop here at step one, we only partially neutralize the sulfuric acid. We didn't completely neutralize it because now we have HSO4 minus. In step two, we could neutralize that last remaining hydrogen if we have enough base. And so here, water wasn't enough to pluck it off, but hydroxide easily plucks off the hydrogen off HSO4 minus, and it's going to make sulfate and water. So in Bronsted, we do it in 2 steps. In metathesis, we just do it all in 1 step. Do you see the difference? In Bronsted, we're neutralizing one at a time. In metathesis, we're going to just completely do both of them. Same time here. All right, so let's take a look at this reaction. This reaction is going to be between sodium hydroxide and sulfuric acid. So I'm going to get my sodium hydroxide here. And then my sulfuric acid. Here. And then see what happens. I saw some vapor. Ooh, it's hot. This is very hot. In fact, you see the steam? There's steam here and it's condensing on the inside wall, the flask, and this is very hot. Water started boiling. So I should have added the acid carefully. I just dumped it in there. It generated a lot of heat. That heat could cause splattering and you could get the sulfuric acid on your hands. And so this is why we have the rule, add the acids. But just because you add the acids doesn't mean you can add it recklessly. That was reckless. I should have added it slowly to make sure any heat generated was dissipated. All right, so there's evidence of reaction because it got very hot. But that could happen just with the water too. pH will tell me as well, you know. But yeah, there's still steam coming off this a little bit. You can see it condense. There's a lot of water vapor condensing on the inside of this. Okay, what's next?
Ammonia and sulfuric acid.
Ammonia and sulfuric acid?
That's the last one.
That's the last one? Okay. Sodium hydroxide is a strong base. Ammonia is a weak base. So do you expect reaction here? Well, let's see what we should expect here. Can I erase this?
Yeah, that's fine.
So we could do this, we might as well do this as a metathesis, right? And so if we use ammonia in a metathesis, I have to add what?
Water.
Water. And ammonia and water will make a little bit of ammonium hydroxide. And so I'll just use that to predict my products. So it's going to be hydrogen with hydroxide. Hydrogen hydroxide is water. And ammonium sulfate. Really this. Is there a driving force for this? What would the driving force for this be? Yeah, and so the stronger acid is sulfuric acid. What's the weaker acid? Weaker acid is water? Yes? Okay, now let's simplify this. Is it balanced? No, I need two ammoniums, right? And so I need two ammonium hydroxides. If I need two ammonium hydroxide, that means I need two ammonias and two waters. And so those two ammonium hydroxides with sulfuric acid, it's going to make two waters like this. Does that look right now? Thanks. Okay, does that look balanced? In other words, I need two ammoniums. So I made two ammonium hydroxides. In order to get two ammonium hydroxides, I use two ammonias and two waters. Does that look right? Okay, and then what can I do? I can cancel the water. If I cancel out the waters, what happened to my driving force? The driving force just disappeared. If the driving force disappeared, that means there's no driving force, that means there's no reaction, correct? Yeah, so there's no reaction. Sulfuric acid plus a weak base like ammonia yields no reaction? No, because you know what happened? What happened is you're in the habit of calling water the weaker acid, but it isn't the weaker acid in this particular reaction. What is the weaker acid in this particular reaction? Water wasn't the weaker acid. Ammonium was the weaker acid. The weaker acid here is ammonium, not water. Because if we go backwards here, who loses the proton? Ammonium to form ammonia. And so be careful, water is not always the weaker acid. And so in this particular reaction, what we're going to have is we're going to have H2SO4 plus two ammonias yields ammonium sulfate. And so this reaction is like a Bronsted acid-base reaction. It doesn't look like a double replacement reaction. And so the ionic equation would look like this. H plus HSO4 minus plus two ammonias yields two ammoniums and a sulfate. So first, the ammonia has no problem plucking this hydrogen. That would be step one in a Bronsted. And then step two in the Bronsted is ammonia has no problem plucking the hydrogen off HSO4 minus. This would be step two. So we have step one and followed by step two. And so this is we originally did this as a metathesis, but this ended up being a Bronsted, in which both steps were combined because we did it metathesis. Does that make sense? Someone? Uh-huh. This would be the ionic equation and the net ionic equation. There are no spectators here. So this would be the CE, this would be the IE, and NIE. The CE looks funny. But that would be it.
Really quick, can you just reiterate why we added the 2 waters to the reactants again?
Okay, because we need 1 water to make ammonium hydroxide with ammonia. And then when we balanced this, it turned out I needed 2 ammoniums. If I needed 2 ammoniums, then I need 2 ammonium hydroxides. But in order to make 2 ammonium hydroxides, we have to start off with 2 ammonias and 2 waters to make 2 ammonium hydroxides. So that's how I ended up with 2 waters there. And then the waters canceled out. Turns out, then we ended up with this equation here. So I can smell the ammonia from this. You might be able to smell it too once it vapors waft towards you guys. But when I add the sulfuric acid, that should kill off the odor because ammonium ions don't smell. Ammonium sulfate doesn't smell. So I'm going to add some sulfuric acid here. There's some heat, not as hot. You know, you don't really see that like in the last reaction. But it is warm. It's very warm, test tube, but not hot. The last one was hot. I don't smell ammonia. I added excess sulfuric acid. Okay with those? That was the last one?
Yeah.
Okay, good. All right.
So going back to the reactions, when I came back the following lab to finish the other one, I noticed some of my solutions in the test tube changed color. Why would that be?
This just has more time. And so there could be some small changes over time. But one of the big things is like crystals. The size of the crystals makes a big difference. You know, the color. So it could have been that. Or, you know, you didn't have complete reaction when you left, but by the time you came back, you had complete reaction. You know, something like that. That's interesting because somebody brought this kind of question up earlier today. You know, a couple of things I needed to talk about. One was, are you guys familiar with a barometer?
Yes.
We're supposed to use a barometer today, but our barometer is broken. I took a look at it this morning. It's not working.
It's always a good day.
Yeah, so we're we'll use something else. So that means all the entries for barometers today, we're going to skip those. Uh-huh. Yeah, scan it to PDF format. This uploaded onto Canvas. Since I just finished today, you could turn it in next week. It's all right. So today we're looking at KClO3. KClO3, I used this stuff in the light bulb experiment. I melted it. But when I melted it, I wanted to be very careful. A couple of things. Because when you look at KClO3, what stands out as far as properties go? You know, what chemical properties really stand out with KClO3? When you see that, you go, yes, that's going to be a strong, what? Strong base. Potassium ions are, well, we'll go back to acid base. Potassium ions are neutral, but this one, what's this called? Chlorate ions are base, but they're so weak, we consider them neutral. It's like chloride. But when I look at this, I see strong oxidizer. How did you recognize that, Tristan? How do you recognize that this is a strong oxidizer?
It can give electrons.
Do oxidizers give electrons, or do oxidizers take electrons? Oxidizers take electrons. Like oxygen. Oxygen takes electrons to form oxide. So is this still an oxidizer or is this a reducer? Reducers give electrons. It's a strong oxidizer. And how can you tell it's a strong oxidizer?
Because the chlorine is +5.
Yeah, here it is. Well, the chlorine's +5, but is +5 the max on chlorine? What's the max? +7. This is not the max, but it's a strong oxidizer. So when I melted the stuff, I had to be very careful. You know, normally when I melt the stuff, I throw in some paper in there, and it just flashes like a little explosive fire. Well, I didn't want any smoke to be generated to set off our smoke alarm or fire alarm, so I didn't do it. But what some people do is they get molten potassium chlorate and they throw gummy bears in there, and the gummy bears go up in a big flash, like a little explosive fire. It's not an explosion, but explosive fire kind of thing. Just rapid fire.
I take it we don't get to use gummy bears.
Yeah, I could do that probably in the hood. Maybe I'll do that one of these times. But what I see is a powerful oxidizer. You know, potassium ions are an oxidizer, but they're one of the weakest oxidizers. So this is a strong oxidizer. So I have to be careful with this. But as long as you separate the oxidizers from the reducers, you're okay, right? And so that's what I did. I tried to make sure that there are no reducers around when I heated this up. Because can potassium ions be further oxidized? No. And so this is okay, this is safe as long as there are no reducers around. Somebody asked me about tannerite. Have you heard of tannerite before? Tannerite is a mixture of ammonium nitrate, this stuff, ammonium, what do we call this? Perchlorate, and aluminum, plus other stuff. So let's compare ammonium perchlorate with potassium perchlorate. Okay, if we compare ammonium perchlorate with potassium perchlorate, they're similar in certain respects. They're both what? They're both strong oxidizers. In fact, but which one would you expect to be stronger of an oxidizer? Potassium ammonium perchlorate or potassium chlorate? Why? Why would you expect this to be stronger?
Because it's +7.
Yeah.
versus +5.
The chlorine here is +7. So this stuff is more dangerous than that stuff, right? But this stuff is even more dangerous than that. What makes this stuff even more dangerous? It has to do with the difference between potassium ions and ammonium ions. They're both +1. They're both soluble when combined with other anions, but their redox properties are quite a bit different. What's different between potassium ions and ammonium ions? Well, potassium ions are an oxidizer, but they're extremely poor. They're very, very weak. They're the second worst oxidizer on the chart. What can you tell me about ammonium? Ammonium is a reducer. Would you say ammonium's electron rich? It's got a positive charge. Would you consider that electron rich?
Yes, 'cause it's N-3.
Yeah, it's -3 on the nitrogen. The plus belongs to hydrogen. That's fine for hydrogen. And so this is electron rich. And when we look at perchlorate is electron poor. The thing that's particularly dangerous about this is you have an electron-rich species and an electron-poor species in the same compound. So what's preventing them from reacting? What's preventing them from reacting is that it's in a crystal lattice. In a crystal lattice, you have the ammoniums in one position and the perchlorates in another. And they can't react because they're kind of locked in their lattice position. But what happens if you start heating this? If you start heating this, then that's going to increase the kinetic energy. And so as we start heating this, the kinetic energy goes up. But do you guys remember that curve? What was the name of the energy distribution curve? The Maxwell-Boltzmann? As we keep heating this up, there's going to be a small population with quite high energy. And if they have a high enough energy, what can happen is they can slam into each other and react. And so this stuff is very dangerous because we have the electron-rich species and electron-poor species in the same, and so we better keep this cool. That is, we can't let this get hot. If this gets hot, it's very dangerous. Whereas if this gets hot, well, I heated it up, I melted it, I wasn't too worried unless I threw in some reducer. For example, if I threw in chunks of aluminum into my molten potassium chlorate, I'm asking for trouble because aluminum is electron rich, and that's going to cause a reaction. And the same thing with ammonium nitrate here. And so for extra good measure, they threw in aluminum in this mixture. Aluminum's a good reducer. So we have a couple of powerful oxidizers. Ammonium's not the greatest reducer. Aluminum is a much better reducer. And so we got plenty of reducers, plenty of oxidizers, we're going to have a reaction. And so that's explosive. In fact, let me show you. Are you guys familiar with PepCon? PepCon is north of Las Vegas.
We're going to find out what happened to the chocolate factory.
Yeah, I need to find out, but I was reading the article and it doesn't say just what happened. Did you guys hear about the chocolate factory that exploded? Was it, what day was that, Saturday?
Friday.
Friday?
7 people died.
Yeah.
They said the explosion was so powerful it made one of the buildings move like 4 feet.
Yeah, here's the article here, one of them. This is the only article I read. It's from LA Times. Bodies of all 7 victims of Pennsylvania chocolate factory explosion have been found. I was thinking this is sugar explosion or chocolate. Is chocolate electron rich or electron poor? Sugar, electron rich or electron poor? Electron rich, right? Electron rich species are good fuels, so maybe something like that. I'm curious what happened. This article doesn't tell me anything about what happened.
If it was a gas leak, then what?
Yeah, it could have been a methane gas leak. We don't know. It doesn't say anything about the cause. State and local fire investigators are continuing to examine the scene to try to determine the cause of the blast. So I don't know. Let's go back to PepCon.
Does a fire extinguisher have the ability to put out all fires or only certain ones?
Good question.
I'm just thinking about it.
Um,
Because I know certain fires you need to handle, like you can't just put water on them, obviously.
Yeah.
You know.
Right. So number one, yeah, water is used to cool things down too. So,
Like an electrical fire or what?
well, not many people have water fire extinguishers anymore, but they still have CO2 fire extinguishers. And if you had a, depends on what you have. If you have a paper fire or wood fire, CO2 is fine because there's no driving force for that. But if you have a metal fire, you don't want to use CO2 in a metal fire. So let's say you have a metal that's on fire, it's burning in O2. Don't use CO2 for a metal fire because CO2 is electron poor or electron rich. It's electron poor. It's not the greatest oxidizer. You know, electron poor species are oxidizers. But metals are easy to oxidize. And so if you use CO2 on a metal fire, it's like fanning the flames, you know, feeding it more oxygen. And so don't use CO2 on a metal fire. Don't use water on metal fires either, because is water electron rich or electron poor? That's not either, but it can be both. It's not a great oxidizer. And so the hydrogens are +1, but they're happy at +1. And it could be a reducer, the oxygen's a -2. But it's not a very good oxidizer. But still, metals are so easy to oxidize because they're so electron rich. We don't want to use oxidizers on a metal fire. And so you don't use water on metal fires and you don't use CO2 on metal fires because those are both oxidizers or potential oxidizers that can just cause additional reactions. So we use other stuff. Halon. Halon might be okay, you know, if you had, I don't know the exact ingredients of halon, but let's say we had something like this. Carbon tetrafluoride. Is carbon tetrafluoride okay? CF4, I'm not going to draw out all the lone pairs, but CF4, is that okay to use? Yeah, this shouldn't have any problem because, well, this is carbon in the +4, but this is fluorine in the -1. But it's, I guess you could say the same thing here. But there are a couple of reasons in addition. The carbon-fluorine bonds are very strong, making this even less reactive. So something like this could work. Yeah, actually, I want to see. let's see what they recommend for extinguishers. Extinguishers for metal. All powder-based specialist fire extinguishers designed for fighting metal fires are categorized as powder extinguishers. What is the extinguisher? Powder. Extinguishers for metal. Specialist fire extinguishers are required to tackle Class D flammable metal fires. Smothering, non-reactive, some inert ingredients, some inert powder to smother it. Sodium chloride fire extinguisher. Sodium chloride's hard to burn. I told you I tried to melt this stuff, but it's hard to burn. Chloride is a really bad reducing agent. Table salt, etc. So yeah, you have to think about the chemistry doing this. Let's go back to this. Back to the beginning. This has the enhanced audio. We don't need the do you need the enhanced audio? Just listen to regular audio. Second part is so much longer than the first part. I couldn't understand why. I thought that was in slow motion.
See, I didn't see no cars leave at all.
No.
Ooh, that's gonna be loud.
So, So one of the students this morning was curious why there were 3 different colors of smoke coming off here. You see that?
So the black the black is basically the carbon.
There's no carbon.
No.
No. This is the why we have the skeleton redox. You know, sometimes you get a mixture of products and it's hard. There could be carbon. You're right. It could be carbon from the building.
Yeah.
Yeah. But in this particular reaction, there's no. So the different colors of smoke could be due from other types of reaction. But that was ammonium perchlorate plant that blew up there. So ammonium perchlorate, this is very dangerous stuff because we have the reducer, electron rich, and the electron poor species in the same container. And if this gets hot, you better watch out because you could have a violent reaction, explosion in that case. There. But with potassium chlorate, that's okay. However, the situation with potassium chlorate is if we continue heating it, then it's going to get hotter and hotter. And then one thing that can happen is this. You know, the chlorines are looking for electrons, and where does it see electrons? Not from potassium ions, but from oxygen. And so this is what's going to happen in this particular reaction. If you continue heating this up, then you got to start worrying about having a disproportionation style reaction. And that is having the oxidizer and the reducer in the same compound. Disproportionation, however, is usually the oxidizer and reducer are the same element. In this case, it's sort of like a disproportionation reaction. And so what's going to happen here is that the chlorine, being in the +5 oxidation state, is going to see these oxygens next to it. And these oxygens next to it are going to be at -2. But oxygen's happy at -2. It does not want to lose these electrons here. But if you heat it up, you know, you're going to make everybody have higher energy. So if you have a high energy chlorine versus a normal chlorine, the high energy chlorine can react more violently. And so as this gets hotter and hotter, what can eventually happen is the chlorine, you know, even though it's not favorable because oxygen is more electronegative, chlorine can actually take the electrons from the oxygen. And if that is the case, then what we end up here forming is KCl and O2 gas. We'll have three halves in O2, 1.5 moles. And so we end up with this. And so this is what we're going to do today. But it's very hard to oxidize the oxygens because the oxygens are very happy as is. And so this reaction, fortunately, is not going to be explosive because it's very hard to do. In fact, it's so hard to do, what we're going to do is we're going to add some catalyst to this. The catalyst we're going to use is manganese 4 oxide, which is this black powder here. And so we'll put in some of this. And the catalyst acts as a way to help speed up the reaction. And so it actually participates, but it doesn't participate in the reaction. So we're going to heat this and add the MnO2 catalyst here. And then this should go. It's still a little bit of a vigorous reaction, so you still have to be careful. If you generate the O2 too fast, what can happen is it can pop the stoppers off. And so here's our KClO3 mixture. It's just this white powder here. And it's not 100% KClO3. The purpose of this is to figure out how much KClO3 is in here. Okay, we don't want to use too much. If we use too much, we'll generate too much oxygen, and we have limited capacity for capturing that. We don't want to exceed that capacity here. So we're going to use about 1.5 grams. And so what you'll do is you'll bring a small beaker to the balance room, zero the beaker, and then weigh the test tube. And then tap in some sample here, 1.5 grams, reweigh that, and then get a little scoop of catalyst, 20 milligrams. There's a test tube in there that shows about how much 20 milligrams is. It could be anything. You get 5 milligrams up to 30, 40, 50. Somebody accidentally got 80 milligrams. It's fine. And then mix it. Okay, then we're going to put it on a utility clamp here and clamp it at the top. We don't want to clamp it here because next we got to heat it up. And you can see, do you see burnt rubber here? Yeah, somebody burnt the rubber on this. So to prevent that from happening, we'll clamp it up here. Every semester somebody clamps it down here and starts melting the rubber, and you can start smelling the burnt rubber in the room. 20 milligrams, but you're not going to measure it. You're just going to get a little scoop. 10 milligrams, they say, is about the size of a small match head. And so if you look at your matches, you know, the match head, the green part is about 10 milligrams worth. And so 2 of those should be enough. But even though we're going to guesstimate 20 milligrams, we want to weigh it. So you're going to weigh everything. You should know how much the test tube weighs, you should know how much your sample weighs, and you should know how much your sample plus the MnO2 weighs. After the reaction, we're going to reweigh everything, and it's going to be KCl plus MnO2. So we need to know how much that weighs as well. So we're going to weigh everything. Okay, then we're going to capture the oxygen. You know, because if we just heat this up, all the oxygen is just going to escape into the lab here. And so we're going to capture it with this apparatus here. And so I have to set up the apparatus. Actually, I ended up, the tubing's so old, I ended up breaking the tubing. And so I'm going to use a shorter piece here. This is the tubing that broke. Oh, you know, you have to clamp this. So I was telling people just to pinch this, like this, to clamp it and clamp it in this way instead. That is to block it, but the tubing was too brittle and broke. Okay, so what we want to do is we want to capture it, and so this is going to be our gas collection apparatus. Our gas collection apparatus is going to consist of this 500 milliliter Florence, this tubing, and a big beaker. And so what we're going to do is we're going to fill this with water. We're going to use tap water for this to save money. You know, DI water is better, but... And it says to use 100 milliliters, but 100 milliliters is too little. Just fill this thing up like halfway. And so do you see I have a flask full with water? Okay, do you see this tube here? This tube, I have to purge the air out of that tube. Like this. So how am I going to purge the air out of the tube? Well, there are different ways we could do this. Okay, this tube's been shortened so it doesn't quite bend where it's supposed to bend. One way is I could use this to blow air. Okay, you don't want to suck the air, so just blow and then blow. But what I'm going to do is I'm just going to cup my hand around the stopper here and just blow this here until I stop seeing air bubbles come out. And so keep an eye on the beaker here, and let me blow this here. Did you see the bubbles? Do you see any more bubbles? All right, then that's the air has been purged out of there. Now, when I purge the air out of there, this is what happens here. Oops. Let me blow it one more time. Do you see I have a huge air pocket now in the flask? So what I'm going to do is I'm going to siphon water back into the flask by holding the beaker up higher. And then I'm going to just raise the water level until it gets to about the stopper. There. Okay, that's good. I don't want to overfill it. And then what I'm going to do is, okay, if this tubing broke again here, If that happens, I have to start over again, unfortunately. This tubing's too old. Okay, once I have the air purged there, I'm going to seal this in here, like this. Okay, and then what I need to do is I need to equalize the pressure inside the flask and outside by making sure the two water levels match. Do you see that? So in other words, with this sealed here, I'm going to siphon water back and forth. If I siphon water back into the flask, that compresses the air in here, and I get compressed air. The compressed air is going to have a higher pressure than outside here. If I siphon water out of the flask, that creates a vacuum, and that vacuum is going to make the air pressure of the air trapped in the flask here lower than atmospheric pressure. So what I want to do is I want to make the two pressures the same. Atmospheric pressure outside pushing down on this, and the gas here, the trapped air, pushing down on this. So what I'm going to do is I'm going to get the two levels equal, and then with the two levels equal, I'm going to pinch the hose so that water can't siphon back and forth. Does that make sense? And then once that's there, then I'm going to dump the water out and then put the tube back in here. And with this sealed here, it should prevent water from siphoning out. Does that make sense? Okay, then once that's ready, then it's good to go. I'll heat this up. You keep heating until you stop seeing any evidence of reaction. So it'll start to bubble, like effervesce, and create gas, and just keep heating it. Again, you don't want it too violent, because if you generate too much pressure at one time, it could pop the stopper off. If it pops the stopper off, then you have to start over again. Okay, then once it's completely reacted, we let it cool down, and then a whole bunch of water will be in here, because what's going to happen is as the oxygen is generated, it's coming into the top of this, and it's going to push the water down out this tube into the beaker. So what we want to do is we want to make sure that the pressure of the air and oxygen that we trap in here is the same as the pressure outside. So we equalize the two levels again, pinch it, and then remove the tube. And this is the amount of water, however much water comes in here, that we just generated from the oxygen gas. And so, so this is what we're going to have here. So inside here, we're going to have some air that's trapped in here. And this air that's trapped in here is above water. There's a whole bunch of water there. And if there's water present in the air becomes humid. And so this is what we call wet air. Wet air is going to have some water vapor, because the water molecules aren't all moving at the same speed. We have a Maxwell-Boltzmann distribution. So some of the water molecules have enough energy to vaporize off the surface. And since the air is trapped in here, this air is trapped in here, we're going to assume that it's become saturated with water vapor. That is, it's become 100% humid. The air in this lab isn't saturated, but we'll assume that the air trapped in here is. And so it's called wet air. And then we're going to generate oxygen. Well, as the oxygen is being generated, it's bubbling through water. What's going to happen as it bubbles through water, it's going to become saturated with water vapor. So that's 100% humid oxygen. And so we have our wet O2. And so what we're doing is we're doing this. This is called Avogadro's law. Avogadro's law. That is the volume of wet air plus the volume of wet O2 is going to give us the volume of the mixture. And so the volume of the mixture is going to be this. It's going to be the cumulative volumes here. And so this will be wet air and wet O2. And so the volumes add up as long as the pressure is the same. So in order for this to work, we have to make sure that the pressure of the wet air is equal to the pressure of the wet O2, which is equal to the pressure of the wet mixture. That is the air plus O2. As long as the pressures are all the same, then the volumes are additive. If one, let's say one's under high pressure and the others are under low pressure, you can't add the volumes. They're not additive. And so this is the reason this works, because any change in volume is due to the wet O2. And so the volume of the wet O2 is equal to the volume of water displaced. So we know what the volume of the wet O2 is. But the problem is this. The volume of the wet O2 is equal to the volume of dry O2 plus the volume of water, vapor. So we know this, but we don't know this. So this room consists of humid air, and so we have dry air and water vapor. So how much of this room is occupied by dry air and how much of this room is occupied by water vapor? And so that's hard to determine. So this is extensive. So it depends on how much this volume is. What we're going to do is we're going to make this extensive property into an intensive property. And then do we need to know? So as an example here, the humidity today is 32% relative humidity. Is that intensive or extensive? 32%. 32%, you know, if it's 100% relative humidity, does that mean the room is filled 100% with water? No, what 100% humidity means it's saturated with water vapor, and it's just a small amount. And so what we're going to do is we're going to assume we have 100% humidity inside that container, and then we're going to do this. This is Avogadro's. Instead, we're going to use Dalton's. This is Avogadro's law. We're going to use Dalton's law. I'm jumping ahead. What we're going to do in this case is we're going to take the volume of the wet O2 and divide it into two containers like this. And so if I have my wet O2, then I'm going to take all the oxygen molecules out of this and put it into the same size container. So this is going to be dry O2. And then what I'm going to do is I'm going to take all the water molecules and put it into a separate container the same size. So this will be my water vapor here. So in this case, the volume of the wet O2 is equal to the volume of dry O2, which is equal to the volume of water vapor. And so I'm going to remove all the dry O2s, put it in the same size container, and remove all the water vapor, put it in the same size container. And so all the containers are the same.
Oh, so this is basically like the Chem 4 experiment.
Yeah, this is Chem 4. So Avogadro's, we say, is constant pressure. So we're doing all this stuff doing the constant pressure. Dalton's, we say, is constant volume. So everything has the same volume. So I know the volumes of everything, but the pressures are going to be different. And so we have over here, we have the pressure of the wet O2. The pressure of the wet O2 is the pressure due to the collisions of the oxygen and the collisions of the water molecules, which we'll do in purple. Here. Okay, then we're going to have the pressure of the dry O2. And then down here we'll have the pressure of the water vapor. And so the pressure of the wet O2, which we know, it's the same as atmospheric pressure. All these are equal to the atmospheric pressure because we get the two levels equal. The pressure of the wet O2, which is equal to the pressure of the atmosphere, is equal to the pressure of the dry O2 plus the pressure of the water vapor. The pressure of the water vapor turns out to be an intensive property. So for example, if it's 19 degrees C or 19.0 degrees C, we could look it up. It's in the table. The table's located in our book. And so this is an intensive property that depends on temperature, and we look it up in the table. And so this is like our percentage humidity. We just look that up. It doesn't matter how big the room or how small the room, it's going to generate the same water vapor pressure. And then we get the pressure of the dry O2. The pressure of the dry O2 is just equal to the atmospheric pressure minus the water vapor pressure. So we can determine how many moles of dry O2 we form. The moles of dry O2 that we formed is equal to the pressure of the dry O2, which we'll calculate from that, times the volume of the dry O2. The volume of the dry O2 is the same as the volume of the wet O2, which is the same as the volume of the mixture, according to this. Divided by RT, divided by RT, the temperature of the O2 is going to be, the dry O2 is going to be the same as the temperature of the wet O2. And so we can get everything to calculate how much oxygen we just generated. Okay, are there any questions for this?
Is this individual or working?
No, you're going to work in
pairs?
pairs. You're going to work in pairs. It's too hard to pinch this, get the levels equal. You need a third hand. You know, somebody to equalize the levels and somebody to pinch the hose. So work in pairs. If you don't have a partner, let me know. I'll pair you up with somebody. And so you'll work in groups of two.